Okay, so hopefully you can all hear me and see the opening slide. So this is an ARCHER2 virtual tutorial. I'm David Henty. I work in the ARCHER2 CSE support team. I'm going to talk about Slurm job submission on ARCHER2. This is actually an updated version of a talk I gave quite a few years ago about the PBS job submission system on Archer. I have a couple of places I might refer back to the differences. It's quite interesting how it works differently. Hopefully, though, even if you're not a heavy ARCHER2 user, Slurm is almost universal now. And so hopefully a lot of the slides and the concept here will be useful even if you're not actually using ARCHER2. So we're using the material, and these are the partners. I would just like to say as well that please ask questions as you go along. I can see the chat here. It's on my screen, so I'm happy to answer questions in chat. Also, this is very much a user's perspective. I mean, I have asked systems review to clarify a few points, but this is really my view of how it works. So it seems to make sense to me. But if there's anything I've got wrong or slightly woolly about, please pipe up if you know better. We can have a chat about it. So a day in the life of a Slurm job. So what you do, the way you interact with a parallel supercomputer like ARCHER2 is you write a batch script with some text editor. So we'll come back to what that means, but you write a job file. I call them .job. People call them different things, but it's just a text file. You then submit that to the Slurm batch system using sbatch. So you don't actually have a log on to the compute nodes, the major computer. You submit this script. Then it's held in a queue until it's able to run, and we'll discuss, why that is and how you can, and what the various aspects of that are. Then it's executed, and that's executing the scripts. But actually, it turns out that the way you launch parallel jobs is a subsequent step, and there's an important difference between when your job starts and when the parallel jobs actually run. And then they're completed and the job output is written and you're done. So that's basically a batch job from cradle to grave. So we'll follow that roughly follow that loop in this talk. So the conception of your job is you write the batch script. Well, what is a batch script? We use that terminology a lot. Well, a batch script is just a list of commands that are executed in order, exactly as if you typed them into the shell on the command line. So you could, one of those is often srun to run parallel jobs. You may set environment variables, you may copy files or do various pre and post processing. So it's like a normal shell script. It's just a whole bunch of commands that you could in principle have written at the command line. And we recommend you use bash. Some people I know use Python, but I mean, bash is simpler here. Now, in a bash script, lines starting hash are comments. However, a common trick is used in all batch systems. Slurm doesn't differ from this. Is that, well, it's a common Unix trick dating back 50 years that there are special comments. So, however you want to pronounce it, hash bang, hash exclamation mark is special to the operating system. So you may see the sentence at the top, hash bang bin bash. That means execute the script via the bash shell. So that's technically a comment that begins with hash, but actually it's interpreted by the operating system to say, oh, this is a bash script. Similarly, you hide Slurm commands in the script through hash sbatch. So hash sbatch is special to the batch system. For example, you might have to say hash sbatch minus job name equals ampersand MPI job. That is formally a comment. So when you run the script, sometime later the script is executed, these are basically skipped, but Slurm interprets them, and we'll come back to why that's a sensible thing to do. So why? Well, some parameters of your job are significant submit time. So the number of nodes and the wall clock time, they're significant submit time because Slurm needs to know them to be able to schedule your job appropriately. But other aspects of your job, setting environment variables, copying, pre and post processing, and all that kind of stuff, is only significant execution time. So it's actually handy to have all of these in the same file. You could specify, and you can in Slurm specify all the parameters to do with the job nodes, time, and things as command line arguments. So every #sbatch command has an equivalent command line argument. But the advantage of having them as #sbatch is you have a single file that contains everything about your job. All the settings are in the same file. And you don't have to pass a huge number of arguments to sbatch. And so as I said, all these parameters are not written on the command line, they're hidden, and you hide these in the script as these special comments. As I said, that means you have a complete copy. If you go back to the batch script, you have a complete copy of all the parameters of your job, which is actually very, very, very useful when you're doing benchmarking for reproducibility. So this hiding special commands as comments is not new. It's been around for 50 years or more. If you're an OpenMP programmer, you know that OpenMP commands for doing threaded parallelism are hidden in C or Fortran files as comments. So a non-OpenMP compiler just skips them. It's the same principle here. So this is the standard example that's on the user guide, and you'll see that we have. I'll go through most of these, but we have a we say this is a special comment to the operating system. Run this as a bash script. And then we say, okay, the job name is this. It's going to run for 20 minutes on 4 nodes. And there's lots and lots of commands here. It's an MPI job. So these are interpreted at submission time, or at least they're pulled out at submission time by Slurm. Then your script runs. As this bit actually runs, we say OMP num_thread equals 1. It's an MPI program. We don't want to do threading. This is a slight quirk since the upgrade. You have to set this variables, and I'll come back to what this means, but this variable here is not automatically passed through to srun. So this is, I don't quite understand why this has changed, but it has changed. But the main point is when you do the srun, you have fairly limited parameters, and things like how many nodes it's running on, how many tasks per node, how many CPUs per task, how many threads, these kind of things are, the things to do with how many nodes and things you're doing are passed automatically from this block to this block. They're actually passed via environment variables, but you don't specify everything again here. You specify the parameters like the number of nodes, how many MPI processes you want at the sbatch. So that's significant at submit time because Slurm knows, or how many processes, i.e. how many nodes does David want, but they're also used at runtime. And that's quite nice. That means the two match up typically. So you don't have to worry that you're not using all the nodes you're allocated because you're running with the same parameters as you specified at submit time. So you might say, great, I've written this batch script. It's got quite a lot of setup, pre and post processing, and run some parallel jobs. If it's just a batch script, can I just run it on the login nodes to check it all works, to check that I haven't made any typos or such like? Well, unfortunately, it's not that simple. Why? Well, your batch script runs on a different computer in a different environment. Your batch script doesn't run on the login nodes, it actually runs on the compute nodes, and we'll come back to that. So you might think, well, some commands that work on the login nodes won't work on the Slurm. Well, that's true, but some commands that don't work on the login nodes only work on the Slurm. So for example, when you launch a parallel job through srun, that works differently from within Slurm than it would do if you just did it on the login node. So you get the different behavior. The other problem is, we'll see later that on the login nodes, you have access to both your home and your work directory. So if you test on the login nodes, it may run, but you may be relying on files or data which are in your home directory, that will not work correctly when you run in batch, where you don't have access to the home file system. And this is particularly true of things like Python and Python virtual environments, which are obsessed with squirreling stuff away in your home directory. It can sometimes be quite painful to tell them not to do that. So that is actually something which is a bit unfortunate, that a lot of systems assume that it can read data from your home directory, often hidden in a doc file. You may not even know it's there, and that is not true on ARCHER2. So that's now the birth of your job is you submit to that system, you type sbatch myscript.job, and immediately you get back a message which tells you your job. So we're up to 4 million jobs on ARCHER2. That's quite impressive, actually. So yeah, I noticed I reran some of my scripts from the early days, and the output was all mangled, and that's because I'd assumed the job number was never going to be more than 6 digits long, so I had to extend that. So I submitted job 4 million 4,015,920. So what happens there? Well, first of all, Slurm takes a copy of your batch script and stores it somewhere in a spool directory. I'm not quite sure where. But it takes a copy of your batch script, okay? So that's important. It also then ascertains the resource requirements, and the most important ones are really the number of nodes and the time you're going to run for, because we'll see that so it gets them from the command line arguments or from your hash sbatch lines, but I would recommend that you do as little as possible in the command line options of sbatch, but do them all in the actual job script, and it returns you this unique job number, which is useful. The job is then queued until resources are available. The job is queued until the resources are available. You can query the status with sq -u my username. SQ by default gives you all the jobs on the system, which blows your terminal. I only found out about a month ago you could do SQ -- me. So I do that all the time now. That shows you your jobs, which is what you normally want. The job status is set to pending PD. So when you see PD, your job is pending. So I mentioned at this point is what you're going to do is that you're probably going to go away and edit your batch script again because Slurm has taken a copy of your batch script. And your batch script has a lot of, I was doing a lot of file system I/O tests, and there's a lot of environment variables and weird and wonderful file system settings. And it's very easy to forget what they were. So what you really want is, you often, if you're interested in performance, you often cannot interpret the output file, the log file from your Slurm job, unless you know the exact parameters with which it was run. So it's really nice to have a copy of your Slurm script in your Slurm output. And I do this now, especially when I'm benchmarking. It means that I don't have to take notes. I'm terrible at taking notes. So I often have my standard job script has a starting context of Slurm job script for job number, and the $Slurm job ID is a magic environment variable which has the Slurm job ID. And cat $0 is the name of the file which bash is executing, and that is it is actually Slurm's copy of your /var/spool/ I don't know what it is, but it is a copy of the exact script which is running now. So I cat that, and I find that really, really useful. And I would have put this in the tips and tricks, but it's relevant here because of talking about taking copies of batch scripts. So often Slurm does this. The submission parameters can be access environment variables, but $0 is the path to Slurm's unique copy of your batch script. So I find this a very useful trick. So whenever I look at a log file from one of my Slurm jobs, I can see exactly what the parameters were. As I said, that's particularly useful when you're doing benchmarking and you're worrying about, or how many OpenMP threads did I do? What were the settings of this? What were that's useful. But that's something for a side at this point. Resource selection. Well, unlike some systems, most jobs at ARCHER2 go to a single queue. I mean, there's really one big queue. There are special queues, but the majority of jobs go to a single queue. Some other systems will have lots of queues routed to, but we have a single queue for most jobs, and that's partition standard and quality of service equals standard. There are some special queues for short and long jobs and higher memory. I'll just mention them a bit later. But the other point is that a check is done at submission time to ensure you have a reasonable budget. So if you have only one compute unit left, which is one node hour, and you submit a job that's going to run for 10 hours on 512 nodes, the system will say you don't have enough. Okay, but it's not foolproof because your job isn't necessarily going to run for the full submission time, and you can submit. So you can go negative on your CU budget, but this is to stop you going incredibly negative. So there are some tolerances there in a check script. But the important point is your jobs are scheduled entirely on the requested resources. I mean, Slurm doesn't know how long your jobs are actually going to run for. All it knows is how long you said it was going to run for. So the job is scheduled based on two parameters: the runtime and the number of nodes, which are 128 cores on ARCHER2. Because parallel compute jobs are always allocated in exclusive mode. So that's all it needs to know. You can specify things like high memory, which is QoS equals high mem, or you can have short, long serial reservation for short job, long job, serial jobs. And you may have set up a reservation, which is reserved nodes. But the ones that I use all the time partition equals standard and QoS equals standard, or QoS equals short for short jobs. So Andy's pointed out that yes, partitions are usually used for different architectures, different CPU types. So the classic thing you might have is you might have a CPU and a GPU partition, which you'll see on Cirrus, our other system, which has both CPU and GPU nodes. So that's useful comment from Andy, thanks. So great, so I can edit the same job script and resubmit straight away. Well, it's not always that simple. What do I mean? Why? Well, if you're running a self-compiled executable, okay, so what you're doing is you're doing submit job, edit executable, recompile, submit. You have to be careful because at execution time, when you do, if I do srun, it will run the executable which is there at that time. Slurm doesn't take a copy of your executable, your actual MPI program. It can't. It doesn't know what you're going to do. So a mistake people make is they do submit job, edit, recompile, submit job, edit, recompile, because actually that you don't know then what executable it's going to run. This is okay if you're running packages, precompiled packages, which essentially installed that don't change, but you have to be very careful if you're constantly compiling and resubmitting. You have to be careful there. How does it decide when to run my job? Well, it's about the requested time, number of nodes in the runtime compared to all the other jobs in the system. Should I take care of specifying? Yes, the main thing is don't ask for huge amounts of runtime if you don't need it. If you're gonna schedule a job that's going to run for an hour, you can maybe ask for an hour and a half. But then Slurm might say, oh, if I look tomorrow morning, there's a half-hour slot, an hour and a half slot, just big enough for David's job. I'll run it tomorrow morning. But if I asked for 10 hours, it would not be able to put it in that slot. So it's very important to try and it's a bit of a balancing act, but to make sure that your requested resources are as close as possible with some tolerance to your actual expected, typically runtime, because the closer they are, the more quickly your job will be scheduled. So don't ask for huge amounts of runtime if you don't need it, because you won't pay for it. We only charge you for what you use, but it means your job will take longer to be scheduled because Slurm will think it's going to be a much bigger job than it really is. So the childhood, okay, we've got a conception about childhood is a set of compute nodes reserved for your job. SQ job takes us to R, it's running. All it means is that your batch job is running. Your bash script is executed on one of the allocated compute nodes, so it just runs your bash script, your Slurm script. But of course, all the hash things are just ignored because they don't mean anything to bash. And where is it run? Okay, this is an interesting question. Where does it actually run? Your script. The script is run serially. It's just run as a single serial script. So it's not run on the login nodes. On Archer, we had special nodes called mom nodes, which were kind of hidden to you. But what Slurm does is it picks one of your compute nodes, and you'll be allocated one or more compute nodes. It picks one of your compute nodes, and what I believe is called the Slurm management node, which I think is always the lowest numbered one, but I might be wrong there. But basically, your bash script is executed on one of the allocated compute nodes, the Slurm management node. So one of your compute nodes is special, and it runs the script. So the only way to access your other compute nodes is via srun. So anything which isn't srun is just running as a serial pre and post processing by default will just run on this management node. So you have to be very careful if you have really, really heavy pre and post processing serial steps, because they'll be running on this single management node, probably on a single core, unless you've been clever, and all your other compute nodes are doing nothing. So we'll come back to a way to maybe circumvent that later. But then somewhere later on, you do srun my MPI program. And all this srun, as I said, inherits all the number of nodes, number of tasks, tasks per node, things you've specified in the sbatch, and they're passed in magically via the background as environment variables. Now, the number of MPI processes accepted is computed from the submission parameters. They can be overridden. You can run with different parameters from what you submitted with, and we'll come back to why you might want to do that. But that would not be the default thing. The default thing is, I think, to specify everything in sbatch parameters and just do srun with a few extra bits we might see later on. So this slide is a bit redundant now, but I'll explain why I left it in. You will have a laptop or a desktop, which is maybe Linux, Mac, or Windows. You SSH onto the login nodes, and they're running a fully fledged Linux. And then srun will launch jobs on the compute nodes. Now, I used to have this little skinny penguin here because on Archer, the login nodes were fully fledged Linux, whereas the compute nodes had a very stripped down Cray Linux environment, CLE it was called. Now, but I was informed this morning that actually, to all intents and purposes, the OS on the compute and login nodes is the same on ARCHER2. So they're much more homogeneous in that sense than Archer was. So this slide is slightly redundant, but I left it in just to illustrate that there is no longer such a stripped down operating system on the compute nodes as there used to be. So the job flow, this is quite important, I think, quite useful to get your head around. So on my laptop, I SSH into the login nodes where I've edited my script and I have my batch job. I then submit it with sbatch, and it is submitted to Slurm, and Slurm takes a copy of it, and then it basically waits for resources. It keeps an eye, I guess it polls the compute nodes and waits for, now I haven't shown you, but this job I've asked for 6 nodes. So at some point in the future, these 6 nodes become available, and we realize we're ready, and at that point your job is run, and it's run, and this magic green node is selected as these 6 nodes as the Slurm management node, and that is the job, the node, the computer on which your batch script runs. And then I said the only way that you can access, or the standard way to access the other compute nodes, is when you do an srun. Your job, your typically parallel MPI job, will be launched on all the other nodes. But the script runs serially on this special management node, and it's the srun command which allows you to run jobs on these. And you're ring fenced. You're not allowed to access nodes outside of the, in this case, 6 you are allocated. So this is now adulthood, parallel jobs. Okay, these compute nodes are reserved for the duration of your job. Slurm doesn't know or care how you use them. So if you don't use them if you run a serial program for 10 hours, Slurm doesn't know. You said you asked for 10 nodes, here's your 10 nodes, off you go and use them. All commands from the batch script are executed on the management node. srun the management node causes parallel jobs to run on all compute nodes. You do production runs in /work file system, not /home, because the /home file system is not available on the compute nodes. However, unlike on Archer, your script automatically starts executing where it was submitted. So on Archer and on other systems I've seen, you always have to do at the top of your Slurm script cd $slurm work dear or something, I think. But on Archer2, your script starts running automatically in the directory from where it was submitted, which is quite nice. And then srun does the following. It launches the executable from all the compute nodes. Now, it reads I thought it broadcasted it. It doesn't. It reads from the file system. So all the compute nodes are reading your executable from the file system, because the file system /work is available to everybody. That could be a bottleneck, and you can use sbcast to explicitly copy the /temp. This is documented on the website. But also srun is to all intents and purposes, the equivalent of MPI run or MPI exec, which you would run on your laptop or on a not quite such an integrated or high scale large cluster. And also, see, when you do an srun, you're maybe launching thousands, tens of thousands of processes. So srun doesn't just launch the jobs, it also gathers the standard error and standard outputs from all those MPI processes and sends them to a single log file. So it's srun which manages that, bring all the data back and write. So when you run, if you do a print statement from 512 MPI processes, unless you've explicitly opened files, all of those will appear in the same log file. How is that possible? Because srun is maintaining that link. So this is how the file systems work. The login nodes can see /work. The compute nodes can see /work, and I've done a bigger error here because the I/O bandwidth from the compute nodes to /work is very big. This is the way that parallel file systems are designed. It allows you to dump data from the thousands of compute nodes very quickly to the many petabytes of parallel cluster storage we have. The logging nodes can see /home, but the compute nodes can't see /home. So you might think the only thing you ever have to do is make sure you CD into /work, but I'm not going to go into the details here. But you can get problems with with anything which wants to read from your home directory, like from a hidden dot file, and that is classic. Python.local is a classic example of that. So I've got from cradle to grave, birth to death. I don't like death. I'm getting a bit old, so I'll call it retirement. The retirement of your job. The job finishes. When does it finish? Well, it finishes after all the commands in the script have been executed, and this is important when I talk about slightly more advanced usage later on. Or the wall clock time is exceeded, at which point your job is actually killed. Slurm will say you've reached your wall clock and it kills you. All running parallel jobs are killed. So if your wall clock is exceeded, when when Slurm decides to kill your job, there's still thousands of MPI processes running. It will kill all of that. Or we'll see you may have launched srun in the background and it will kill those as well. I'll see that. But basically, Slurm tidies up everything. The outputs are all collated and flushed to file, and they're written to a job. Now, by default, Slurm does append the job number, so that's quite nice. The log file has a record of your job number. The sbatch job status is set to CG for a little while. I didn't know what CG meant, but it means completing, not completed. CG for completing, not the world's most obvious acronym, but anyway, and then a little while later it will disappear. There's some tidy up done at the end, tidies up, and there's a lot of management tasks and things to make sure the node is a bit of, it's like paying your Airbnb turnaround fee. It's got to change the bed linen and make sure everything's spick and span for the next user to come along. So you are charged for the number of nodes you requested, regardless of whether you actually used them, because you're denying anyone else using them. So it's kind of, unfortunately, it's your fault if you don't use them. And the minimum allocation is a node, and the serial queues are shared, but I'm not going to talk about them. For the majority of the compute nodes, they're reserved exclusively for a single user, which is nice. That gives you reproducible performance because you know that nobody else is running. You're charged for the amount of time your job ran, regardless of how much time you requested. So the advantage of requesting a job runtime, which is only slightly more than your actual runtime, is that your job will run quicker, will be scheduled quicker, sorry, not run quicker. A job that is killed due to running for too long is still charged. So if you run out of time and don't write the output file, you'll get charged and you've wasted your time, unless it hung due to a system error. So if you can prove that it was a system problem, not yours, you can request a refund. But it is important to note that if a job runs to the end and doesn't produce output, if it just ran a bit longer than you thought and you ran out of time, I'm afraid you've still used the nodes. So how does srun place processes and threads? Well, this is quite a complicated question, but I'll show you what I use and what is recommended in the documentation and what I understand. The key parameters you can specify are in the sbatch section, nodes, which is the number of nodes, tasks per node, how many MPI processes are there per node, which is normally 128 because you have 128 CPU cores, but could be different. N tasks is the total number of tasks you're going to run. So if you're running 1024 MPI process, it would be 1024. And CPUs per task is how many CPU cores are allocated to each task. Now, there's some redundancy here. So if you said nodes equals 4 and tasks per node equals 128, it's the same as tasks equals 512 and tasks per node equals 128. So from both these, Slurm could work out at submit time you need 4 nodes. Yeah, that's obvious because it's explicit. That's obvious because it's calculable. If you specify incompatible parameters, Slurm complains, and it has some rule for taking precedence. Or sometimes we'll say, oh, that's not compatible, but I'm ignoring one of these. But I would always try and make them incompatible. But really at submit time, as long as Slurm's got enough information to work out how many nodes you need, it's fine. At submit time, that's all that matters. At runtime, it's more complicated. So how does srun place processes and threads? We recommend srun minus hint equals no multi-thread, minus distribution equals block my MPI program. So as I said, most of the parameters that you specify in the sbatch section are passed implicitly to this command. The one exception is this CPUs per task, and you'll see we recommend export srun CPUs per task equals $slurm CPUs per task. You only really need to worry about this if you set this to be bigger than 1, but I would recommend leaving it in anyway, because it's no harm to have it. So why this? So if you just do srun, Slurm has some way of distributing the processes amongst the nodes and the cores on the node, which is slightly hard to understand. Well, I like this because this does what I would expect. It places MPI processes sequentially across each node. So it fills up the first node before moving on to the second. So it just packs them in and fills the nodes up in order. So that's quite straightforward, okay? So, you know, MPI ranks 0 to 127 are placed on the first node, 128 to 255 on the second node, and such on. Each process is given CPUs per task CPU cores. So, for example, if you said CPUs per task equals 2, and assuming you had a very large number of tasks, it would give, this gives CPU task equals 2 gives 64 MPI processes on each node, because it's spacing them out, but not by 1 by 2, but on the even numbers cores of each node. So if you specify CPUs per task equals 2, it will specify that it will run the MPI process on ranks 0, 2, 4, 6, 8 up to 1, 2, 6. And srun pins the processes. They're locked down as much as possible, which is what you want. They're actually located and told to stay there. What is this strange minus hint equals no multi-thread? Well, we actually have hyper-threading. So actually there are, Linux thinks that each node on Archer 2 has 256 CPU cores, because each physical core can run 2 programs, 2 threads at once. But we don't, for HPC, it's rare that that's useful for reasons we could discuss after. So we really want to just use, so the numbers 0 to 127 are the physical cores, 128 to 255 are the hyper cores, and they match up. So core N and N plus 128 are the physical core, and the sort of hyper core, are a pair of these hyper cores on the same physical core. But the way Archer 2 numbers them, the first 128, 0 to 127 are all the physical cores. So minus hint equals no multi-thread. Don't use the hypercores. So this is basically what I would recommend for people. The only complication is why would you spec? Well, the thing I haven't explained here is why might you ask for more than 1 CPU per MPI process? Well, there are 2 main use cases for that. One is you need more than 2 gigabytes per core. So you might want to say, well, you know, each core needs almost 4 gigabytes, so I could only run 64. Sorry, each MPI processor needs 4 gigabytes. I can only run 64 of them on a node, on a standard memory node, so I have to skip every other core. Or you might be using OpenMP. If you're using OpenMP, you are subsequently going to spawn OpenMP threads, and you need to leave cores empty, which are not running MPI processes, to be filled up. So if I would MPI OpenMP, you should set OMP num thread equal to CPUs per task. Now you can do that by hand, or you can actually do export OMP num threads as $slurm CPUs per task, which is quite useful. Makes sure they're the same. I said that Slurm binds the MPI process. That's because it does it at launch time. But once Slurm has launched your processes, they're away and running. And in an OpenMP, the parallel threads, so all the parallel processes are created by srun, but the OpenMP threads are created at runtime when you hit a parallel region. So they may not be scheduled. So you have to also say OMP places equals cores to ensure the correct binding of threads. But that's the standard recipe, and there's an example in the documentation. This can all get a bit complicated, but there's a magic program called XT-High, which we inherited from Cray, but my colleague Kevin Stratford has maintained now a lot. And all this does is it prints out the nodes and the bindings of each process or thread within each node. So if you're unsure of what's going on, you have srun blah 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 my program, we'll just do srun blah 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 xt high, and xt high runs and says, hi, this is where we're all running. And it prints out either a number, it says I'm running on CPU core 8. It might print out a list. Look, I can run on, this is saying I can run on anywhere on the same physical core. I can run on core 3 or core 131, which is a core and hypercore. Or it gives you a range. It says, look, I'm not bound to a core, but I'm bound to a range. I can run on, and it will do it. So that xt high, modulo xt high is very, very useful. Thanks to Kevin for maintaining that. So finally, I'm talking about some things you can do with srun. You can issue multiple sruns in a single job. You often don't, but you can. And a single job but many sruns can be better than many small batch jobs. And there are two reasons why that is. One is benchmarking, and one is task farms with multiple concurrent sruns. So what you're going to do here is that at runtime, you're going to specify a different number. You're going to mess around with things like how many nodes and how many tasks you're going to use. So the way I recommend doing that is specify minimal resource requirements at submit time. Just say how many nodes you want. And then you should specify all the other parameters as arguments to srun. And you have to be very pedantic here. You have to specify them all. Otherwise, funny things happen. So if I wanted to run, now imagine I've asked for 4 nodes, but at runtime, I don't want to run on 4 nodes. I just want to run on the first 2 nodes. I would do srun minus nodes equals 2, which overrides that value. But also I want to do minus n task equals 256, minus tasks per node equals 128, minus CPUs per task equals 1, minus distribution of block. But you have, I would specify all these parameters here, because if you miss some of them out, they are often inherited from somewhere else or computed in a way you don't want. So whenever your srun parameters are different from what the defaults you would expect, I recommend you specify them all, and that works. So why might you want to do this? Well, benchmarking. Often you want to do a scaling run. You want to run on 128, 256, 512, 1024 processes. It'd be nice to submit a single job that requested, in this case, 8 nodes, and ran all those jobs in a oneer. 4 sruns, srun. And so what you would do is you do a single sbatch with number of nodes equals 8, and then you do srun minus nodes equals 1, 2, 4, and 8, and vary these parameters accordingly. So that allows you to do a single run where you run on 1 node, 2 node, 4 node, 8 nodes, but in a single batch script. That's advantage A, there's less queuing. You queue once, your job is scheduled, you get all your parallel scaling. But also for performance measurements, all the jobs run on the same set of nodes, so performance is more reproducible. You have this set of nodes for the whole job, and you're running on the first, the second, all of them. The disadvantage, of course, you pay for unused resources because you've requested, in this case, 8 nodes. But I mean, if you're doing a benchmarking run, you will have dialed back the runtime anyway. So this is a very useful trick for benchmarking runs. It allows you to do a single sbatch and get all your scaling data out in a single file. The other thing is a task farm. So imagine that I've requested 4 jobs, and I actually have a bunch of jobs that actually only run on 2 nodes. Okay, so I think I could actually run 2 of them at once. Okay, so let's.
Okay, can you hear me, please?
Yeah.
Okay, thank you. I was checking because I'm interested in these multiple sruns.
Yeah.
What do you actually mean by multiple srun? Let's say, for example, I have a Slurm job that I want to run 2 TPR files. Can I run them using just only one Slurm job submission, or I have to create 2 different Slurm document for them?
Right. Well, I think I'm going to explain that here actually. So maybe I'll wait. I think the next few slides maybe explain that. So okay. I'll show. Yeah. Julian, for benchmark, the less reproducibility the same node, I know they're having that in a single job. I would not. Well, you can't select nodes on ARCHER2. We don't let you ask for nodes. You can't specify a node file on ARCHER2. That is you can't do that. So you're right. If there was if you're running on a system which allows you to request specific nodes, then yes, there's no difference between the two. But on ARCHER2, we don't allow you to request nodes. So yeah, I think does that explain that? Hopefully that. But that's a good question. But it don't allow you to. Yeah, fine. So what I'm saying here is I've got a job which only uses 2 nodes, but I've requested 4. So I want to run, and I've got 4 of these. Okay. So what I want to do is I want to run this on each of these runs on 2 nodes, and I've requested 4. So what I hope is that these first 2 commands run on 2 nodes. These run using all the 4 nodes, and then when they've finished, I can then process dataset and dataset 3 and dataset 4. So I've got 4 jobs here, each using 2 nodes. I've requested 4, so I'd hope they'd run 2 at once, okay? And so I'd have 2 running at once, and then they'd finish, and the next 2 would run. That's not going to work because srun blocks. So srun, well, these would all run sequentially. So what would happen here is that dataset 1 would be processed on the first 2 nodes, and then it would wait. And then, so this is not what you want to do. I want to have more than one want to have more than one copy of my program, or of the parallel job my program, running at once. So what you have to do is to run them in the background. So you have to say, I run that in the back. That means that after that srun is launched, it immediately launches this. So you have 4 sruns executed at once. And what you're hoping is that the first 2 are scheduled to the first 2 jobs. Each of these running on 2 nodes are scheduled to the 4 nodes. They run, and you hope these other 2 sruns will wait till the resources are free. Srun here acting like a mini scheduler, and then will be launched. Now that is possible, but this doesn't work. Quite weird reasons is that this job finishes after all the commands in the script have executed. So basically, it runs through. The script gets to the end. It says, "Oh, I finished running the script," and it ends. So you can't do that. You can't run them all in the background. You might think, well, I'll just run the last one in the background. Isn't that fine? That's not fine either, because the script finishes where dataset 4 finishes, but possibly dataset 3 is still being processed, and then dataset 3 job will be killed. So that's a bit of a list. The way to do it is this, okay? The way to do it is this. Run them in the background. So you launch 4 sruns. You think, I've got 4 nodes. I want to run 4 jobs, each of which uses 2 nodes. You tell srun that you want to do all that, and then you have this magic command wait, which says don't go past this line in the script till all previous spawned jobs have completed. And srun is being really cleverly act like a mini. The first srun says, okay, I could process dataset 1 on the first 2 nodes. The second one says, oh, I can fit them in the next 2 nodes using all 4 nodes. The third one and the fourth one say, oh, there's no nodes free, so they wait. And then one of your jobs will finish, and the next one will launch in there. And so srun is dynamically allocated, just like sbatch does at a much more higher level. Within this single sbatch, single Slurm job, srun is doing this. It's like a mini task file. It's scheduling them all around, and that's really quite a nice thing to be able to do. And I've seen people do that. So you want to run lots of small jobs in this on lots of nodes. You can do a single sbatch and do this. This only works for full nodes, though. This is a slight technicality, but if you wanted 8 jobs, each using 64 processes each, okay, you might do this, okay. However, what srun does is it assigns the entire node resources to each program. That includes all the memory. So what it will do here is it'll run dataset 1 probably on node 1, dataset 2 on node 2, dataset 3 on node 3, dataset 4 on node 4, dataset 5. Well, there's enough, half the CPUs on node 1 are unused, but unfortunately, Slurm thinks you're using all the memory, so it will block. So the solution is a rather ugly thing, but you have to specify the memory requirements of your program as well. Say, look, I only want 2 GB per process. Well, dial it down a bit, because you probably only want 1.5. So this is what I really ought to do there, is I do the same thing before all this stuff, but I say -1 is exact. You don't explain exactly what that is, as I can't remember, but you say -1 memory equals 1500 megabytes. You're saying each of my MPI processes only takes 1.5 gigabytes. And so when it comes to dataset 5, it says, oh, there's 64 CPU cores free on the first node. Oh, and enough memory. I will schedule the job on there. Okay, so it's slightly complicated, but I've tested this and this does work correctly. This is all documented in the manual, in the documentation, I should say. So that's really all I had to say. I had a couple of tips and tricks at the end. It's useful to have print statements appear in the log file ASAP. As by default, Slurm will buffer things and only flush the output every now and again. That could be annoying if your job crashes. You may not have all the output from your job, and so you may not know where your job was because there's half a dozen lines still missing. So I tend to run with minus unbuffered. Minus unbuffered says flush the standard outputs from all the processes to the .out file as soon as they're ready, which I find useful. You can also do interactive jobs, allow you to do real-time experiments. If you're oh, so yeah, that's nice, Andy. Thanks. Yeah. So Andy said you can you get the estimated start time for your job, which is so Slurm at submit time will say, when do I think I can run this job? That will obviously change over time, but it has a good guess at the start, and that can be very useful. To do an interactive job, it allows you to do real-time experiments with many S-runs, but single S-batch. So, for example, if you're debugging, you have a deadlock, you want to run, recompile, run. That's useful. Or in principle, you can debug your batch script to check all commands are correct. You would like to be able to run your batch script to see what it's doing to check all pre and post progression things that are correct. So what you essentially do is you submit a parallel job. What it does, it runs a terminal. So this is what you do. I'm on the login node. Oh yes, so Harvey's saying unbuffered is useful if you run something interactive that crashes. Yeah, otherwise you might not see the error at all. Yeah, that's very important. Yeah. So we do srun. We do an srun, okay? And what it does is it requests 2 nodes, and it actually says I just want to run the bash job. So when this is scheduled, you're allocated 2 nodes, but you get back a prompt, okay? But how can you tell you've been scheduled on over? Well, hopefully you have a cursor which tells you where you are. You see I'm now on node whatever, one of the compute nodes. So I'm now on the management node. So once you do this, you can then do lots of sruns. So I use this when I'm debugging a program, which doesn't work. I do a single srun to get some resources, and then I'll compile srun. If it deadlocks, I can control C it and keep looking for the problem. There's been a change, I believe. So if you want to debug scripts, you might want to start with a clean environment. By default, this bash shell inherits all your environment variables from your log where you started on the login, and you may not want that. But I think there's been a change since the upgrade. You need to do --, over subscribe for subsequent sruns to srun a job. I think that's been a change. Slightly awkward, but final one. This is one you may want to run a bash system command on every compute node. Okay, you might want to monitor memory usage or CPU load. So I'll answer that question. Yeah, I'm almost finished. That's a good question, Yanis. I'll answer that just in a second. The approach is put it in execute. So if you want to run a system command like top, I want to run top -b. That just runs top once. Top tells you what's happening on this node. But I don't. If I just run top in my batch script, it will just run on the compute node. Sorry, the management node. I want to run this on all nodes. Okay. So what I do is I put it in an executable shell script, okay, call it top.sh, and then in my script I run 1 copy per node. I do srun minus tasks per node equals 1, minus n tasks equals $slurm n nodes, minus nodes equals $slurm n nodes. I'm being a bit pedantic here, but I'm over specifying everything. /top.sh, and that will then run this command, which is a bash script on every node, and that can be very useful if you want to look at what's happening on every node. You can srun a command and do that. So Yanis asked, can we use salloc ARCHER2 job load? Oh, for this particular command, it will be easier, but you could do this for, I've used this for doing a parallel zip, for example. So I wanted to do a zip on every node because I've had a zip command, which is very heavy duty. I don't want to run it just on the management node. I want to run it on all nodes. So yes, there are people like Andy have packaged up various scripts for doing this, but this was just an example for for this question. So Yanis, can we just use SR? Yes, you can. I didn't put that in because there's a slight subtlety to it, but what I will do is my last slide, sorry, the next slide was are there any questions? Apologies, I ended slightly early. But what I will do is I'll stop sharing my sorry, I'm getting slightly lost here because I have too many emails to me. I will share a window. Is that showing? Yes, so we do ARCHER2. So it's here. So you can use srlock, but the strange thing about srlock, so if you do srlock and then srun, you can do that. But when you do srlock, you stay on the login node. You don't end up on the computer, which so I don't know what it's not really quite the same. So you can do that, and the advantage is I think you don't have to do -- over subscribe when you do srun, but it's different. I would, if you do srun directly, you end up on the sorry, the srun comes first. Yes. Anyway, that's the difference. You can use srlock, but it's slightly different, and I don't know what the pros and cons are of that. I've never used it myself. Does that answer your question, Yanis? So yes, you can. Yeah. Okay, so I was going to open up for questions now. I'll leave the web. So are there any? I hope I've not missed any questions. Oh no, I think I have. So okay. So you're trying to run. Well, you need to. So okay. So you're doing something different. You're using an array. You're doing array jobs. So array jobs are yes. So that will run. Yes. Task per node. No, that will run. It will run math. It will run 6 copies of math simulation, each on a different node, and you're using the job array feature of Slurm, which I haven't covered here. However, it will run them serially. So you're running one serial math simulation program on each node. I don't know if that's what you want to do, but that's what it will do. Yes, one MPI process per node. So you're running math simulations serially. So you're running one copy of math simulation on each on its own node. Yes. So that was my question. I'm wondering if it's threaded. I did, but by default that will run one process per node, which may or may not be what you want to do. But you're right, it will run 6 simulations each on a separate node. Does that answer your question? I mean, the CPUs per task doesn't say use 128 CPUs. It says space the MPI tasks out by 128. So it's up to you. I don't know what math simulation is, whether it's got. If math simulation isn't threaded, then you will be wasting 127 cores on each node. If math simulation is threaded, then you'll be fine. So maybe you need to look a bit more deeply into that. But it is. I think it's doing what you. Yeah, I understand what it's doing. Yeah. Are there any other questions? I'm happy to take questions now, or if anything occurs to you after the end of the slot, which is right now, actually. So yes, Andy said here, 108 threads will often perform poorly. Reckon maximum of 16 threads for performance. That's because the the way that the ARCHER2 nodes are constructed, they are effectively 8 mini processors, each with 16 cores. So that's what they are effectively. So and for memory locality reasons, as exactly as Andy said, your sweet spot is unlikely to be more than 16. It could be less, but 16. Yeah, you're right. So you would normally not run any fewer than 8 processes per node. And you might, but the sweet spot is normally something like 8 processes per node. Your go-to configuration would be 8 processes per node. Well, actually, yes, the best is 4. Yes, you're right. Yeah, Percy. Yeah. I think they share L3. I can't remember if 4 CPUs core share an L3, but there are various thresholds. Yeah, so there's a nice web page there. Yeah, okay, 4 cores share 1 L3 cache. Any other questions? If you think of any other questions afterwards, please feel free to submit a query to the ARCHER2 help desk. It's there for anything you want to. Kasim's got a question.
Yep. Just a quick one, please. I'm just checking. Do we have the GROMACS installed on GPU in ARCHER2?
Well, we don't have GPUs on ARCHER2, so GROMACS is installed, but the GPU features won't have been enabled because there are no GPUs on ARCHER2, at least not for production.
Okay.
On our Cirrus system, we have GPUs, so you could run GROMACS using GPUs on Cirrus, which is also a national system, smaller than ARCHER2, but yeah, so we don't have GPUs on ARCHER2 currently, so no, GROMACS won't run on GPUs. Sorry.
Okay, I just want to get access to the other system, please.
So the other system is called so if I go to so yes, a copy of the slides will be available. They may be a bit messy because the PDFs, I've got quite a few animations, and the PDFs from animations can be a bit mucky, but hopefully not too bad. So yes, so that's the URL. So this is this is our web site and access, academic access. So Cirrus, that'll tell you how to access this. Lots of ways of getting access to Cirrus.
Okay.
And the hardware is, what is the hardware? Cirrus hardware. So we have, 36 compute nodes, each with 144, yeah. There, 144 GPU nodes. Yeah.
Okay. Thank you very much.
Seems like, okay, so seems like, but we're just over time actually anyway, so thanks everyone for attending.
Thanks, David. That was really excellent.